So we've played around with this rate of change, average rate of change um, process. And so this is the formula that you learn in pre-calculus. It's a big old nasty fraction, h on the bottom. The top is the difference of two values of f, one at x plus h and the other at x. And this is also the change in y, the difference in the two y values over the change in x. And what we were doing is using h as a horizontal change, and it was small. And what we found out was that when we were doing this with logarithm using Sage Math, when h was really small, the two different secants that you got, one from going right and one from going left, started to have about the same slope. So we need to pin down what that process is, and then we'll be able to use that to do, well, this is like one of the most fundamental things in calculus, so we'll use that. So what we saw was that this was settling down when h was near 0. I've rewritten it with some colors because I want to emphasize the role of h. And remember, h can be both positive and negative. And I'm going to put a notation in front here that is a very common thing, and then I'll explain what this notation is. So the process that we went through for looking at what happened when h was near 0 is called a limit, and it's the limit for h near 0. Now, everyone else in the universe says h goes to 0. H isn't going anywhere. This is for all h's near 0. So I want to emphasize that in this expression, the real variable is h. So we pick an h, make sure it's near 0, and then evaluate what is going on here. So this limit process is a little bit easier to understand. It is never easy to understand, but it's easier to understand if we abstract it a little bit. So let me write a slightly different version that we can play with. So this is the more general abstract thing. So what I've written here in green is limit x near a of f of x is L. And so x is near a, x is not going to a, x is not at a. And what this means is that we're guaranteed that when x is near a, f of x is near L. So I'm going to write that down. So let me kind of help you parse it out here. So this is a working definition of limit. F of x is near L whenever x is near a. Now, there are all kinds of exceptions that can come up, and so in the 3-semester calculus courses, you start to go into a lot more detail about this as far as using it for logical purposes. But for a 1-semester course where we're focused on applications, let me just show you what goes on. It's not as mysterious as people have made it sound. And so let me give you a couple of examples. So limit for x near a of x, so that's the function f of x equals x. The function just gives you back the input. And so the puzzle is, oh, if x is near a, what is x near? A. If x is near a, then x is near a. That's a silly way to say it, but that's the way that limit goes. So if x is near a, then we're guaranteed that x is near a. No big woo. Okay. There's another strange one, and this can be very confusing. If x is near a is just some point on the number line, and f of x is 7. So this is the constant function 7. This is the function that whatever you do just says 7. It's like a spoiled child. And whatever you throw in, it says 7. That's a function. It's not an interesting function, but it's a function. And so if x is near a, f of x is near 7. It's at 7. So the limit of a constant function is just the value of that constant function. Not necessarily a real mysterious process. There are some funky things that you can do, and we will in fact have to do them very quickly. And that involves, if you're taking a limit of a quotient, and if the top and bottom both have limit 0, well, that's how I got this scar in 8th grade. And so we have to do some special things there. Actually, it's nothing to do with limits. We just have to do algebra until the limit becomes obvious. So these are the obvious limits. The function f of x equals x. The function f of x is always 7. There it goes. So just to put this into action, let's look at limit x near 3 of x squared minus 4. And so that's the way it would appear. The reasoning is this: if x is near 3, this is not mysterious, then x squared is near 9. What's the big mystery there? I don't know. And that means that x squared minus 4 is near 5. And that's really all we have to do these limits, is this kind of reasoning right here. Okay. So let's go back to the secant lines and the average rate of change. And now we're going to go back to, that's with this pink stuff, we're going to go back and look at the limit of the slopes of the secants. That is, first of all, geometrically the slope of the tangent line, if there is one, which there almost always is. And the limit is something we've already seen in a lot of ways. And so let me write this down. And so it's limit h near 0 of, frankly, it is a big old nasty fraction. H is on the bottom, and the top is the difference between the two values of f. That's what makes it the change in y. And you see I'm doing the parentheses first here. So I've said, oh yeah, it's going to be a value of f and a value of f, but I haven't actually put in where we're evaluating f. So now I will. And so that's at x plus h in the first case and x in the second. So that's what we were talking about when we were doing these average rates of change for h very small. So now we're saying, well, okay, actually what we've done there is taken the limit, and that limit has a name. It's called f prime of x, and this is the derivative. That's a new word. That's calculus, is derivatives. It is the instantaneous rate of change, because it's the limit of the average rates of change. You'd think you could write the word instantaneous instantaneously. And it is the slope of the tangent at the point where you're looking. You see, x isn't changing in here. H is the only thing that's changing. H is near 0, and then so we focus on a particular x. So this is the slope of the tangent. And when we were looking at tangent line approximations, we were just estimating the slope of the tangent. Now, this gives us a way to perhaps calculate it. And so this makes this ability to do the tangent line approximation much more accurate. And so let's play with that now. And so here's the deal. Oh, let me write down some things about the way we write derivatives. So we can talk about f prime of x. That's an interesting notation. It says, oh, we got f here, but we've done something to it. So that's the prime to indicate that there's a difference. There's another notation which looks like a fraction. It is not, but it looks like a fraction. It is df by dx. This notation is due to Leibniz. Some people write this as dy by dx. That depends on saying that y is equal to f of x. And some people, sometimes you just say d by dx, and you just, instead of giving a name to the function, you just write in a formula for it. So you say d by dx of x squared minus 4. So that's not equal, but it's the same kind of notation thing there. So this is the way we write it down. The great thing about the Leibniz notation is it tells you what the variable is, which can be important in a lot of applications where there are parameters that are not varying. So it's good to specify what the variable is, and there's the deal. Okay. So let me go back and see what was happening when we were looking at average rates of change for logarithm over very small horizontal intervals. And the pattern that emerged there, and this is the correct pattern, is that the derivative of the natural log of x is 1 over x. That's what makes it natural. The derivative of the natural log of x is 1 over x. And so the natural log is like, you can't really calculate that. We're just going to approximate it. But you can do the derivative exactly, which is pretty strange. And so what we're saying here is, let me give you kind of a cartoon graph of y equals natural log of x. And let's pick out a couple of points. So at the point 1, 0, natural log of 1 is 0. So that's one of the points that we can actually calculate the log. So this is at 1, 0. The slope of the tangent, I'll draw in a little tangent here. So there's a spot on the graph of natural log, and the slope of that tangent line, instead of eyeballing it like we were doing before, we can say the slope is, be careful here, the input is 1, so the slope is 1 over 1. There's another step involved to say, well, 1 over 1 is 1, but in fact, you don't want to destroy the pattern, and so you say the slope is 1 over 1. You can calculate it later, but you always need to organize and then calculate. If you look where x is 2, I'm going to write an approximate value. Natural log of 2 is about 0.69. That's worth knowing. And so we have a tangent line there. So let me show you what we're talking about. So instead of writing natural log of 2, I wrote the approximate value that I've memorized and found very useful over the years. And I've drawn the tangent line, and the slope is, it's just 1 over 2. The input is 2. The slope is the reciprocal of the input. So the slope is 1 over 2. And so we can talk about values of the natural log using the tangent line approximation near 2. And if we look a little bit further out, I'm going to have to give you kind of a ... here. Using the properties of logarithm, if we go out to 1024, 1024 is 2 to the 10th. And so the actual value of the function there is 10 times the natural log of 2, because the natural log of 2 to the 10th is 10 times the natural log of 2. So that's approximately 1024, 6.9, 10 times 0.69. And the slope of the tangent there, I don't know where I could left myself room to write it, so I'll just put it down here. The slope of the tangent there, for natural log, the slope of the tangent is 1 over the input. That's what makes it natural. And so we have an easy calculation of the slope, even though calculating the actual value of the log is difficult. So that's why we say when x is big, natural log of x is growing very slowly, is growing like 1 over x. When x is 1,000,000, the slope of the tangent is like 1 over 1,000,000. So if you're doing the tangent line approximation, you're not adding anything as you move a little bit horizontally. So let me finish by showing you something very interesting about this natural log. And this is at 1, at x equals 1. We'll do the tangent line approximation. And so the tangent line approximation says, oh, look, we've got this point 1, 0, and we know the slope of the tangent line, and we know the tangent line stays very, very close to the function if we don't move very far away from 1. So the tangent line approximation says that y minus the natural log of 1 is approximately 1 over 1 times x minus 1. Now that's kind of a funny way to write it, so I'm going to simplify it. But that's when you're doing the point slope form, right? You don't do anything. You don't calculate anything. You just rearrange the data. Y minus the known y value is approximately the slope times x minus the known x value. So that's one of the advantages of the tangent line approximation, is that you don't actually calculate anything. But here, let me do a little bit, because natural log of 1 is 0. And so what we have is, and 1 over 1 is 1. This is one of the places where it's worth doing that. So what we find here is that if x is near 1, y is approximately x. Sorry, I jammed this in here a little bit. Y is approximately equal to x if x is near 1, which means, for example, that the natural log of, say, 1.02, I'm sorry, I wrote x minus, well, we're fine. X is the difference, and so the natural log of 1.02 is approximately 0.02. And the natural log of 0.99 is approximately minus 0.01. That's the tangent line approximation, and we can now do that exactly. And what we're going to do is find some general rules for working with the most common functions and be able to find slopes of tangents, derivatives, instantaneous rates of change exactly. And then we can use the tangent line approximation and other tools once we know what that slope is.